Hello. Well, how are you? I hope you enjoyed the lunch. Let's start with the third block of ENAEM. And for this block, we have three speakers. The first speaker will be Mauro Bonfanti from Mauro Lab, Politecnico di Torino, and he's going to present halfway between frequency and time, a spectral domain solution to the modeling paradox.
Thank you, Facundo. I hope you're still alive after lunch, so I can be quick as possible. I am presenting a work that talks about joining some frequency domain methods to nonlinear time domain representation, just to find a sweet point in the modeling paradox. Enhancing the powerful of numerical modeling while reducing the time consumption. So the case study is ISWEC, as Giuseppe presented this morning, is an inertial-based energy converter. This video regards some experimental test did in Naples almost 10 years ago. It is composed by a sealed hull containing a spinning gyroscope. The precision most of the gyroscope is generated by the oscillation of the hull, and some fancy characteristics is that is modular and scalable, is a safety because no mechanical parts are in contact with the marine environment. And then we can just also see a GIF of a concept for with one only gyroscope. The full-scale device has two gyroscopes inside it, and you can see here the full-scale device deployed in Pantelleria almost 8 years ago. So about the technology for the power conversion, ISWEC can implement a mechanical power takeoff. So it's basically a classic transmission with some mechanical gearbox and an electric generator, and then some more articulated power takeoff that is composed by an hydraulic converter, a control manifold with some valves, safety check valves, sensor, oil filter, and so on, with two filtering accumulation, an hydraulic motor, and an electric generator. These two power takeoff concepts have some cons and pros. Especially the hydraulic power takeoff can handle more powerful sea with basically commercial components. On the other hand, the mechanical power takeoff can enhance the controllability of the system, basically because there is not accumulation. So there is not basically the coupling between the controllable part and the power extraction part. So what about modeling? Professor John Rigwood introduces the modeling paradox a few years ago in his work, and we can have from the two sides of the box the frequency domain representation. So this is basically fully linear. We can derive a straightforward control action, control strategies, and then is easy to derive and very fast to simulate. On the other side, we can see a general nonlinear modeling. So we have some linear components on the right of the equation, then plus a nonlinear contribution, generic, and as we can see, we can have different effects regarding nonlinearities, like viscous damping, mooring, and stop mechanism for the power takeoff, some hard stop from the damping side, nonlinear hydrodynamics, and so on. So, can we find a sweet point? Basically, yes. So, try to confuse you about with some analytical formulation, but basically we can bring the nonlinear term, derive some equivalent, let me say, linear representation of the nonlinear dynamics. So that basically maps the nonlinear contribution in a frequency domain. Just wrap it into the linear contribution and then derive the linear transfer function between the wave force and the WEC motion. This process is iterative, so you can start the simulation with a guess of the equivalent contribution, make some results. With the results, derive a new equivalent representation, get new results, and going on until the process converge. So basically, as you can see, we can obtain two similar plants. The second one, so the spectral domain one, just wrapped up all the nonlinearities in a statistical way. So iterative procedure to find equivalent matrix depending on the system outputs. So here is briefly the nonlinear equation of USWEC. You can find, in this case, a linear hydrodynamics, a nonlinear gyroscopic coupling, and a nonlinear power takeoff. Especially the power takeoff is kind of a mess because we have two kinds of saturation that works together. Torque saturation that basically limits the power takeoff torque acting on the gyroscope shaft, and then power saturation that limits the achievable power. So we can basically define a piecewise constant, non-differentiable power takeoff torque, and then with some cumbersome algebraic operation, we can derive a linear statistical representation of the nonlinear contribution. Without going to details, as you can see, the linear contribution depends on the power takeoff parameter, so K and C as basically the linear coefficient depending on the power takeoff speed and power takeoff position, and then this huge integrator that depends on the limit of your power takeoff. So it depends on the ratio between the power saturation and the torque saturation, and also depends on the motion, or to be precise, on the standard deviation of the motion of the gyroscope. So as the standard deviation increases, for example, this original linear coefficient is decreased just to account that the power takeoff is not able to give you enough power, enough torque. So just trust me, the analytical process is correct. And so you can see the spectral domain as a correction between the full linear part of the power takeoff, that is basically the first relation, and the nonlinearities. Here are some results. So we simulate the nonlinear system, the spectral domain representation, just varying the damping coefficient of the power takeoff, the saturation of the power takeoff, and the saturation, the torque saturation and the power saturation. As you can see, as the nonlinearity increases, the accuracy of the spectral domain decrease further, but as you can see, with medium size, medium magnitude nonlinearities, the spectral domain accurately follow the nonlinear behavior. The most striking result is that the spectral domain model is able to reduce almost 2 orders of magnitude the simulation time, and I didn't report the frequency domain results, but basically you can imagine that the frequency domain doesn't take into account any power takeoff saturation. So the frequency domain basically can't see any effect of the saturation, and is only able to linearize the gyroscopic effect. So now we have a linear representation of the nonlinear behavior of our system, and we can basically make some fancy control. So a new work by me and Nicola Faedo, one of my colleagues, is to wrap up the impedance matching principle into the spectral domain representation. I will be quick about this. The impedance matching is a kind of control that make a feedback law that basically make a resonant the system in all the frequency with respect to the wave input. So we can derive the transfer function between the wave force and the wave velocity, make some like inverse operation and find the optimal impedance matching control transfer function. That it can't be used in practice, so we just make a workaround. So we can basically interpolate the control transfer function in one frequency, or the work of like Professor Ringwood with light cone fashion or something similar, and get an optimal single point PI control with respect to the WEC speed. So we changed the case study. We consider a fully nonlinear point absorber. As you can see, there are different nonlinear contributions. The nonlinear stiffness defined here, the viscous damping defined here, the hard stop mechanism of the power takeoff, the snap throat mechanism that is used like a tunable moving system to enhance the frequency, to enhance the motion of the device, and the saturation of the PTO, and a Coulomb-like friction, so like full of nonlinear effect. And what we do basically, we use the frequency domain model of this plant, the spectral domain model, and the time domain one. So the operation was to find three control methods, so three control tuning method, in order to identify the PI control parameter. So basically, the control of the PTO is linear with respect to its position and linear with respect to speed. The linear part with respect to speed is used to extract power, and the linear part with respect to the position is to enhance, make the system resonant with the incoming wave. So the three methods regard the use of impedance matching principle with the frequency domain representation, the impedance matching principle with the spectral domain representation, and the last one is an exhaustive search. So basically, we can parametrically search for each combination of alpha and beta just to find the best one that extracts the most achievable power. All these parameters are applied to the nonlinear plant. So we basically compare three different methods to tuning a PI controller with respect to the nonlinear plant. We test it with the occurrency table and energy table of Pantelleria, and especially in these three C states. So some results. As you can see, the method one that concern the impedance matching method tuned with frequency domain model and applied to the nonlinear plant, we can extract almost 150 megawatts hour per year with a CPU time of tuning and simulating about 0.022 seconds. The second one regards the use of spectral domain to derive the PI controller. So as you can see, the power extraction is remarkably improved because since that the spectral domain can map the nonlinear behavior, synthesizing an impedance matching basic control with the spectral domain representation is more accurate than use frequency domain one, and the CPU time slightly increased. And then we can see that, of course, the best power extraction comes from an exhaustive search that takes a lot of time compared with method 2. So the third method concerns, again, an exhaustive search. So I try for each wave any possibilities, almost, of course, any possibilities of alpha and beta, and I pick the best one. And, of course, this method takes a lot of time. So basically, the spectral domain is useful to simulate the system with a certain degree of accuracy with respect to the frequency domain, but most important, reducing the CPU time. Moreover, we can use the spectral domain to synthesize like an almost optimal, towards optimal control, bounding the time again. So just leave you a couple of publications. The message that I want to deliver with this presentation is that The design of WEC is becoming as holistic as possible, so considering all the factors of the process, so the mooring system, the power takeoff saturation, the power takeoff cost, the hydrodynamic as non-linear as possible. So to better improve the HCOE, we have to approach the design of WECs in a holistic view. With a holistic view, we have a bunch, like billion of combination of your design parameters, so you have to cut off the simulation time with a variable numerical tool and optimal control strategy. Yeah, that's all.
Good. Well, thank you very much, Mauro. This was a great presentation. Is there any question? Well, we had two.
Thank you, Mauro. I was wondering, taking a look at the one of the final images that you put there, I was wondering that one. How do you analyze the? How do you connect actually the great power that you can actually extract with these new methods, but also compared to the C state that you're actually analyzing? Because I can see that state CS2. Actually, the extract power is rather. I don't know if you can mention something about that.
I'm not sure if I understand correctly, but basically the first chart refers to the power extracted with respect to the 3C state I showed here. So it's just like 3 single C state example. The right axis, colored in red, is representing the ratio between the power extracted with the method 3 with respect to method 2 and 1. So as you can see, method 2 approaches the method 3 in power extraction, and then is able to reduce between like 3, between 4, 3, and order of magnitude the computational time. The left chart is just like 3 waves of example which are, that are then re-simulated in the wall scatter table, and then the right chart represents the global energy extraction difference between method 1 and 3 and between method 2 and 3. I don't know if I answered to you or...
No, but the point is that if you can take a look at the extracted power in state S2, actually there's not much improvement when you compare every model. And instead you have like a great improvement in state S3. Is that correct? State S3, there's a huge difference in the...
You mean that there is no a lot of improvement using method 2?
Exactly. So I was wondering, what can you actually say about that?
Method 2 is not optimal.
I'm sorry, not method, the C state. Because you have more power when you change the C state. So how do you link actually the connection with the C state that you're using and the
and the behavior of the control? Okay. As the C state becomes bigger, the nonlinearities increase. So the method 2 becomes like low. Yeah, sorry. Because like low accurate, because the nonlinear effect gets bigger, and then the spectral representation losing accuracy.
Thank you.
Okay, we have time for one question. I think Marcos was raised hand first. Oh, that's okay, it's it.
I was wondering when you presented the statistical equation when you obtained the derivatives.
I think.
There.
Sorry.
Yeah, you use the standard deviation in the equation.
Yeah.
So you assume that the variable that you are observing is normal. It has normal distribution.
Yeah. The spectral domain underlies a new probability distribution of the input as well as the output. It's not mandatory to be Gaussian, just Gaussian, let me say, just simplify the derivation of the process, but you can use basically each probability distribution, and yeah, as you know, the expected value of the derivation of a function is just the function itself integrated over the function of probability. So the Gaussian form, you can see the Gaussian form basically from here, and yeah, so but you're not you have not to consider all the Gaussian distribution. You can basically use each type of distribution you fit to the problem.
Okay, so you fit the distribution to a Gaussian.
Yeah, I suppose that the C state can be represented by Gaussian distribution, and then I derive the Gaussian assumption. But yeah, you're not constrained to Gaussian distribution.
Okay, thank you.
Okay, thank you very much, Mauro. You have